Hello, now we move to the last part of this topic, which is on feedback. This time around, we'll look into the positive feedback and what is Barkhausen criteria. Positive feedback is actually introduction to an oscillator. An oscillator is just an electronic circuit that produces a periodic waveform, and what it needs is just a DC supply voltage. So you just need a DC power supply voltage over here, and the output can be a sinusoidal waveform, or it could also be a non-sinusoidal waveform, which is square wave or triangular wave depending on the circuit. Positive feedback is actually the basic for an oscillator. It is characterized by no net phase shift or 0 degree or 360 around the loop. Okay, so we look into details on this later. Basically, for example, if you have an inverting amplifier, okay, when it is an inverting amplifier, when you have a signal VI, your output signal will be out of phase of your input. So this is your VI, your output is out of phase by 180 degree. And in positive feedback, we have also a feedback network. We take the output voltage, goes to the feedback network, and we fed it back to the amplifier over here, creating feedback voltage. So since the amplifier is inverting amplifier, the feedback network must introduce another 180 degree phase shift so that your VF, which is the output of your feedback network, this is the feedback voltage, will be out of phase with the output signal. Okay, but your VF is actually your Vin, and both are in phase because this is the same signal. Okay, and the amplifier will amplify the input signal. So if you look over here, the amplitude is much larger compared to Vin, but for the feedback network, it is attenuator where the output signal will be attenuated. So the feedback voltage over here, the amplitude will be less compared to Vout. So with this, by having a 180 degree phase shift by inverting amplifier followed by another 180 degree in the feedback network, we have a total 360 phase shift around the loop. This is important for a circuit with a positive feedback to be an oscillator. And suppose that you have a non-inverting amplifier, what will happen? Okay, we look into this. This is your Vin. So your Vin and Vout will be in phase. The only difference is your output will be amplified by this amplifier. And again, we have a feedback network. So the feedback network does not have to introduce a phase shift. We take the Vout, and your feedback signal, which is your voltage over here, will be attenuated by the feedback network. The amplitude will be less between VO and VI, but the phase is similar. So your VF and VI are in phase. So this is for a non-inverting amplifier. There is no phase shift introduced in the loop, or it is a 0 degree. From the figures that have been shown, you have a feedback voltage, which is also the input signal to the amplifier, will produce an output voltage, and in turn will produce back the feedback voltage. So meaning that there is a loop created, and with this, they will produce a sinusoidal waveform, and we have an oscillation. Okay, and the condition for oscillation is you must make sure the phase shift around the loop must be 0 degree or 360 degree depending on the amplifier just now, whether it is inverting or non-inverting. If non-inverting, you don't need to introduce a phase shift, but if it is inverting, you need to introduce 180 by the amplifier and another 180 degree by the feedback network. Okay, and the gain around the loop, which is the product of beta multiplied with A, must equals to 1. These two conditions are known as Barkhausen criterion. This is example of non-inverting amplifier. So non-inverting, the phase shift will be 0 degree. Your output over here will be in phase. There is no phase shift around the loop. And A multiplied with beta over here must equals to 1. These two must be met before the circuit can be an oscillator. So for inverting amplifier, if you look over here, you have an output which is not in phase with the feedback signal, which is the input to your inverting amplifier. Okay, so you need to introduce a phase shift around the loop, 360 degree, 180 by the inverting amplifier, and another 180 degrees by the feedback circuit. So the total phase shift will be 360. And the closed loop gain is, if you look over here, A multiplied with beta must equals to 1. Okay, this is in order to sustain an oscillation. I have mentioned that oscillator does not need to have an input source. What it needs is just a power supply, which is your VCC. At the time t over here, once you connect the circuit to the power supply at t0, what will happen is several sinusoidal waveform will be created by the circuit. Okay, and this sinusoidal waveform will be amplified and fed back to the feedback network. The feedback network will choose one of the frequency and feed it back to the amplifier. And if you look over here, okay, so it will be amplified again and again. This is when the condition of A multiplied with beta is greater than 1. Okay, when it is greater than 1, it will be amplified again and again. But once it reaches 1, which is A multiplied with beta equals to 1, they will produce a steady state sinusoidal waveform over here. Okay, so this is the condition just now I mentioned, beta multiplied with A must equals to 1. Okay, now we look into the effect of beta A if the value is not equal to 1. For example, I have amplifier with a gain of 100 and my beta is 0.1. 100 multiplied with 0.1, I get beta is 10, which is greater than 1. What will happen is, since it is greater than 1, because this is a closed loop, it will be amplified again and again until it saturates. So there is a clipping at the output because the limit for the peak to peak of your output signal will be limited by the power supply. So there is a clipping over here. This is when beta A greater than 1. We don't need this. Okay. And then we look into when A, for example, this time around still 100, but your beta is 0.005. So beta multiplied with A is 0.5, which is less than 1. What will happen is you will see that the output signal will getting smaller and smaller and eventually it will dies out. Okay, so there is damping, meaning that the output will be fading. Okay, also we don't need this to be happen. And if you want the circuit to be an oscillator, beta multiplied with A must equals to 1. So your AV 100, beta is 0.01, producing a beta A equals to 1. And with this, you'll have a steady sinusoidal waveform. Just now I have showed the startup. The startup is actually occurring over here. And it is occur at a very short time before it will produce a steady state sinusoidal waveform. So, in this topic, I have shown the connection between positive feedback and oscillator. Oscillator use a positive feedback, but in order for the circuit to be an oscillator using the positive feedback technique, it must satisfy the Barkhausen criteria, which is beta A. Beta, the feedback network, multiplied with the gain equals to 1. And the phase shift around the loop must be 0 or 360 degrees depending on the type of amplifier. With that, we conclude the topic of feedback, and we'll continue in the next lesson, which is a positive feedback. Thank you.